All right, welcome. So in this video, we're going to talk about a theorem, or our first real theorem of the year. It's called the squeeze theorem or the sandwich theorem. It has two names. The name's not as important as sort of what it does, because what it's going to help us do is sort of evaluate some limits that maybe we didn't think we could evaluate. So let me talk about what the squeeze theorem says, and then I can let you know what we use it for, actually. So the squeeze theorem says that, well, it has a condition. So the setup is that you have to have three different functions, and one of the functions is always in between two of the functions. So that's what we have here. So suppose that f to g, which is less than or equal to h. So I have a couple graphs here where h is higher than f or equal to f in a bunch of different places. So let's go ahead and sketch in g. So in this particular case, if g has to stay between f and h the whole time, then, you know, let's say this is g here. Y equals g of x. So in a case like this, this sort of case is not very helpful. If we know that f is between, or g is between f and h, we could write a statement that says something about, well, we would know that the limit as x approaches a of f of x is going to be less than or equal to the limit as x approaches a of g of x, which will be less than or equal to the limit as x approaches a of h of x. And we can see that that inequality has to be true. So if you just sort of grab a random point here and call that a, well, then you can see if you go up, f approaches this value here, and g approaches that value, and h approaches that value, so h is bigger than g, which is bigger than f, which is what this is saying right here. Which isn't superbly helpful. It's not what the squeeze theorem is really there for. I mean, this is sort of kind of what the squeeze theorem is telling us. It's more interesting when something like this happens, where you know that h is going to be bigger than or equal to f, but at some point, perhaps, h and f intersect each other right here. So now if we were to draw g, knowing that g has to stay in between, so g can be up here, and then perhaps, you know, squiggling a bit, but it has to go through this point here, and then voila, like so. And let's say that that little place where it all sort of smashes together is A, and that place where they all smash together is, let's call it capital L for limit. That's the limit. So now this statement becomes a little more interesting here, because what it's saying is that, well, we know that g is in between f and h the whole time. And we have this added fact that h and f have the same limit of L at some point. And so this is sort of like the most ridiculous statement ever. I'm thinking of a number between 2 and 2. Like, what number am I thinking of? Well, it'd have to be 2. So in other words, what the squeeze theorem says is that if you know this is true, that g is in between f and h all the time, then the limits have to be between each other as well. And if these two limits on the outside here approach the same thing, there's nothing happening here other than g going to L as well, since it has to be in between or equal to. So that's kind of why it's called the squeeze theorem, is like you're kind of looking at the graph and it sort of like seems like it's squeezing g in between them. It's not really, but that's sort of the idea. So the conclusion would be that the limit of g as we approach a has to be L as well. And you might be thinking, well, like, duh, it's obvious. You just look at the graph and you can see that g is approaching L. The graphs, or the equations we're going to be dealing with, the functions we're going to be dealing with, the graphs aren't as obvious. But like, you can usually find obviousness on the outside. Like this thing, this limit, you'd be like, I don't know how to do that. What skills do I have? But then you're like, oh, like I can figure out how to deal with the things on the outside. So let me show you an example of using the squeeze theorem. So oftentimes you'll see that like the squeeze theorem problems have you sort of verify a limit. Like it'll say, show that the limit of blah equals 2. This one we're just going to do from scratch. I'm not going to tell you what the answer is, and we'll just get to it from there. So here we go. So we want to evaluate the limit as x approaches 0 of x squared times sine of 1 over x. So we want to evaluate that limit right there. So let's do a false start. Let's do this in a way that maybe you would think to do it, which would not be using the squeeze theorem, and see sort of why we got some issues going on here. So what if somebody goes, well, like let's just limit law it up, limit laws. This is going to be a wrong approach, okay, just FYI. So they might go, great, the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine of 1 over x. Cool. So like this first one is very obvious. It's just 0, so great. This next one, well, let's think about that. So x is getting smaller towards 0. So this would be the same thing as sine over 1 over a small number. I'm not paying attention to the sign at the moment, but obviously you should be thinking about like, well, isn't it like negative on one side and positive on the other? Yeah, that's true. Okay, so then 0 times sine of, and now this is just a big old number headed towards infinity, one of the infinities. Well, now wait a minute. We saw this in class. We had cosine of x as x approaches infinity. That's basically what this is saying. Like this on the inside is going to infinity. So what is sine doing? Well, sine is just oscillating between -1 and 1. It's not approaching an actual value. So in this case, 0 times does not exist. Well, wait a minute. You did a math hospital problem just about this. You don't want to say that this doesn't exist. You don't want to say it's 0. You don't want to say anything about this. This just makes me sad. Like it's like, ugh, I didn't get anything. I didn't conclude anything about this. So let's see how sort of squeeze theorem can come to the rescue. So this is bad. No good, very bad, don't do it. Let's squeeze theorem it up. So over here, let's do this in a better way using the squeeze theorem. Okay. So the thing I want to do here is I want to think about bounding my equation. And you know what the easiest thing to do is? It's actually sort of the leap I made from here to there. That's the idea behind how I start this. I talked about how sine is always oscillating between -1 and 1. Sine of anything is always oscillating between -1 and 1. If you start getting, vertical translations and vertical dilations and reflections, that obviously could change, but this doesn't have any vertical anything's going on there. It has this weird 1 over x on the inside, which is what's causing the issue. So basically, sine of 1 over x is always going to be bigger than or equal to -1, or smaller than or equal to +1. And if you don't believe me, like graph this thing. You can also see what's happening to this thing as you get close to 0. If you wanted to pause the video, go to Desmos real quick, graph sine of 1 over x, and just look at what it's trying to do near the origin. Whew, it's weird. Okay, so this is a good start. We've got an equation, we got it bounded, or an inequality, it's bounded on both sides here. Of course, this middle part here is not the actual limit we want to try to find. So let's actually do this. I'm going to go ahead and multiply every part of this by x squared. So I'll get -1x squared times x squared sine of 1 over x. And on the other side, +1x squared. Cool. So since x squared is always positive, no weird flippity flops of signs. Okay. So now I have in the middle the actual expression I want to find the limit of. So at this point, let's just find the limit of it. So we're going to go the limit as x approaches 0 of negative x squared. That's got to be smaller than or equal to the limit of x squared times sine of 1 over x. And that's got to be smaller than or equal to the limit of as x approaches 0 of just positive x squared. All right, so now the middle is the limit I'm trying to evaluate, which I had no success on. However, these are quite simple to evaluate. They're continuous functions, they're parabolas. One of them is reflected over the x-axis, the other one's just the parent. And I know that as I approach 0 on both of these, the y value also approaches 0. So what I found out is that the limit I'm trying to evaluate must be greater than or equal to 0 and less than or equal to 0. So quick, I'm thinking of a number between 0 and 0. What's the number? Well, the number's got to be 0. So I found out that the limit as x approaches 0 of x squared times sine of 1 over x has to be 0. And you can graph that in Desmos along with it. I'll do a quick sketch down here just to sort of finish off the video. So basically, if you graph it in Desmos, this is going to be a very quick sketch. What you have here is you'll have y equals x squared up top. And then you have, oh, wrong color, y equals negative x squared down below, like so. And then in between, so now if you actually graph this thing here, y equals x squared times sine of 1 over x, you get, it does this thing. It goes like this, bounces back and forth, 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 like so. Oh. So yeah, it's kind of cool. Like it, oscillates, but the oscillations get wider as it goes along. And it stays in between the two parabolas the whole time. And since the two parabolas, quote unquote, squeeze together at 0, that means that this expression here has to be approaching 0 as well. Cool. So there it is. Let me know what questions you have by taking the survey. Please take the survey. Some of you have been sort of not doing it. And don't worry about clicking turn in. I just need your name in the survey, and that gets you the credits. Will be the first video that goes for credit, so make sure you actually do this one. Okay, thank you very much.